In this session we will be learning subgraph, induced graph, spanning subgraph and isomorphism concepts. So what is a subgraph? For example, if I consider a graph, say here I have considered a graph with A, B, C, D, E edges, right? Then I can call that as a graph, right? This is the graph G. So if G is equal to V comma E is a graph, directed or undirected, then G1 is equal to V1 comma E1 is called as a subgraph of G. Means here I have a graph G. This entire thing we call it as a graph, right? So now here I have taken only the vertex A and vertex B. Vertex A and B, this forms a subgraph, right? And we have I have considered here E, D and C. This forms a subgraph. So here a graph G1, which is nothing but a set of vertices in V1 and set of vertices in E1 is called as a subgraph. So here if phi is not equal to V1 means if the vertex is 0, then we don't consider that as a subgraph. So V1 should be a subset of the entire set V and E1 should be a subset or equal to the entire set E here, where V1 is the vertices and E1 is the incident edges, right? So here we have considered one edge and two vertices, so this I can call it as a subgraph, and here I have considered three vertices and two edges, I can call it as a subgraph. Similarly, here I have considered all the vertices of the graph with minimum number of edges, right? So here since all the vertices are considered in the subgraph, then we call it as a special subgraph, and that subgraph we call it as a spanning subgraph. So in case of spanning subgraph, we will have all the vertices that are in graph G, right? So that is why I have told here if V1 is equal to V, means the set of vertices in the subgraph should be equal to V, then we call it as a spanning subgraph. So let us see the definition of a spanning subgraph. A given graph G is equal to V comma E if there is a spanning subgraph G1 is equal to V1 comma E1 of G such that V1 is equal to V, then G1 is called a spanning subgraph of G. Or we can also tell that if in a subgraph, if all the vertices are part of the subgraph with minimum number of edges, then we can call it as a spanning subgraph, right? So here the subgraph G1 of the graph is a spanning subgraph of G whenever G1 contain all vertices. This is very important, where G1 contains all vertices of G. Thus a graph and all its spanning subgraphs have the same vertex set, right? Then we call it as a spanning subgraph, right? So here I have considered G1 is the graph which contains 4 vertices, right? And here G2 is a graph which contains 4 vertices, right? All 4 vertices are available, but the number of edges, right, that is from V1 to V3 is missing here. But still, since all vertices are available, we can call that as a spanning subgraph, right? And here G3 contains only 3 vertices, whereas the graph contains 4 vertices. Since G3 contains only 3 vertices, we cannot call it as a spanning subgraph because one of the vertex is missing here, right? So G is the given graph, G2 is the spanning graph, and G3 is not a spanning graph, right? So here for a given graph shown, G2 is a spanning graph and G1 is the spanning subgraph and G2 is only a subgraph, not a spanning graph. Next comes induced subgraph. So here given a graph G, V comma E, suppose there is a subgraph G1 that is equal to V1 comma E1 of G such that every edge A comma B of G where A comma B belongs to V1 is an edge of G1 also. Then G1 is called an induced subgraph of G. So induced by V1. So here I have considered a graph that is with 5 vertices, right, and I call this as G. And here I have considered G1 with 4 vertices, right. So I have taken V1, V2 I have considered, V3 I have considered and V5 I have considered. So these are the vertices that I have considered, right. These are the vertices that I have considered, and for these vertices, right, all the edges that are connected to these vertices are part of G1, right. So here in G2 I have considered the same set of vertices, but the edge V5 to V3 is missing here, right. But in the original graph, right, there is an edge V5 to V3 and this edge is missing. So this graph G2 is not induced graph because the edges are missing, whereas the graph G1 is called as induced graph because all the edges related to these vertices have been induced in graph G1. So I can call graph G1 as an induced graph and G2 is not an induced graph. Let us see one more example here. So here I have considered a graph with these many number of vertices, right. So here a graph with V is equal to 6 vertices, right. So now as we in the previous slide we have seen, null vertex will not be part of an induced graph. Induced graph are represented using U, right. So null vertex is not the subset of V, right. So the subgraph of G induced by U is the subgraph whose vertex set is U and which contains all edges from G, right. So now here I have considered a graph. This is a subgraph. Now we need to check whether it is an induced subgraph or not. So here I have considered vertex 1, 2, 3 and 4. So vertex 1, 2, 3 and 4, right. So from 1 to 2 there is an edge, that edge is considered. From 1 to 3 there is an edge, that edge is considered. From 1 to 4 there is an edge and that edge is considered here. So since all the edges that are related to this vertex have been considered, so we call it as an induced subgraph, right. So here I have taken the same subgraph, but the edge 1 to 3 is missing, right. This edge is missing. So this cannot be an induced subgraph, right, whereas this graph is an induced subgraph and this is not an induced subgraph. Next comes the complement of a given graph. So let G be an undirected graph having n vertices without loops. The complement of G denoted by G bar, this is G bar, consisting of n vertices in G and all edges are not in G. So this is the graph G, right, which contains 4 vertices, right, and this is G bar. G bar contains the complement of G. See here the vertex V1 to V2 there is an edge, that edge is not considered here. V2 to V3 there is an edge, that edge is not considered. V2 to V4 V2 to V4, that edge is not considered. Means the edges that are available in G are not in G bar, that is the complement. The edges that are not in G are considered in G bar. Means here the edge V1 to V3 there is an edge, V1 to V4 there is an edge. So the complement of G is G bar, which contains two edges V1 to V3 and V1 to V4. So this is the complement of a given graph. So next we will see some more definitions with respect to the degree of a given vertex. Degree of a vertex is an undirected graph. The degree of the vertex in an undirected graph. So here the number of edges incident on V with loops counted twice denoted by degree of V, right. So here I have considered a graph. So here I need to find the degree of V. What is the degree of V? Since I have taken an undirected graph, right. So here the edge incident at V1, 1, 2, 3, 3 edges are incident at V1. So the degree of V1 is equal to 3. So here the degree of V3 is equal to 1, the degree of V2 is equal to 1, degree of V4 is equal to 1. So since here we have considered an undirected graph, right, there is no in degree and out degree, right. We need to just consider all the edges that are incident at that vertex, right. So the degree of the vertex is discussed in two cases. In the first case, degree of vertex is in an undirected graph. So here I have explained for an undirected graph. So here the vertex V1 is having degree 3, vertex V2 degree 1, vertex V3 degree 1, vertex V4 degree 1. So next case we will take for a directed graph. So the degree of vertex in directed graph. So each vertex has an in degree and an out degree, right. So here I have considered our graph with 3 vertex, right. V1 is having in degree, means that is incident towards this vertex, that is 1, and the edges that are moving out is 1. Similarly for vertex 3, 1 in degree, 1 out degree, and similarly for vertex 2, 1 in degree and 1 out degree. The same is mentioned in the table here. In degree for V1 is 1, V2 is 1, V3 is 1, and similarly out degree for V1 is equal to 1, V2 is 1 and V3 is 1. Next we will see graph isomorphism. So let us see the definition first. What is graph isomorphism? So let G is equal to V1 comma E1 and G2 is equal to V2 comma E2. We need to consider two graphs, G1 graph and G2 graph, be two undirected graphs. So here I have taken undirected graphs. A function f that is mapped to the vertex of V1 to the vertex of V2 is called graph isomorphism if it satisfies the following condition. So first condition is a function f which is mapping to the vertices of V1, that is vertices of the first graph to the vertices of the second graph should be 1 to 1 and on to. It should satisfy the function property 1 to 1 and on to. And the second one, for all a comma b belong to the vertex V1, a comma b belongs to the edge E1 if and only if f of a comma f of b belongs to E2. F of a comma f of b, this is the edge that belongs to the edge E2. When such a function exists, G1 and G2 are called isomorphic graph. Let us see that with examples. So here I have considered a graph, right. This is G1 and this is G2, right. So here we have A, B, C, D, has 4 vertices and we have 6 edges. Similarly, I have one more graph with 4 vertices and 6 edges. Now we need to check whether these two graphs are isomorphic. So to check whether these two graphs are isomorphic, first I need to check whether there is a function from the vertex of G1 to the vertex of G2, and that function should be 1 to 1 and on to. So here if I consider A vertex and if I map this A vertex with the V vertex, right, because the edge E1 is mapping to the vertex, E1 is an edge between A and B, right. So now I need to consider, I need to map the vertex A to vertex U, right. So if I am able to map the vertex A to vertex U and B to the vertex W, then the edge E1 will be mapped to the edge E1 in graph A and in the first graph and in the second graph, right. So here that I have shown here. So f of A is being mapped to U, f of B is mapped to W, f of C is mapped to V, and f of D is mapped to X. Means A is mapped to U, B is mapped to W, and D is mapped to X, and C is mapped to V. Now we have all the 4 vertices that is been mapped to all the 4 vertices in graph G2. So now the graph G1 and G2 defined by the function f, that is 1 to 1 and on to, correspondence between ABCD and UVWX, and both graphs are complete graph, hence they are isomorphic graphs, right. So here they preserve the adjacency and also they preserve the cycle and all the paths that are part of the graph. So we can tell that the two graphs are isomorphic graph. So that we'll see with more examples here. So here I have taken 2 graphs. So let us, here this is figure A, figure B, right. So isomorphic graph preserves all adjacency. So if I am considering 2 vertex A and B, so I am mapping A to U and B to W and the edge, right. So the edge between U and W is E1, and similarly the edge between A and B is E1 and its adjacent edge is E3. So here also its adjacent edge is E3 here. So it preserves all the adjacency with respect to edge and with respect to vertices. So it also preserves graph substructure such as paths and cycles, right. So that we will see with an example here. So here A comma C, A comma C, C comma D, C comma D, D comma A, D comma A. So constitutes a cycle of length 3. So we are having a cycle here of length 3, right. The same thing can be considered here also. So from A to C we are moving from U to V, V to X and X to W. So here also we have the same length 3, right. So which constitutes a cycle of length 3, right. And next is the path. Sorry, here the cycle. The cycle means here we need to connect B to A as well. So here I am connecting W to U as well, right. So it forms a cycle of length 4. It forms a cycle of length 4. Here it should be length 4. So this is also of length 4 and here U to V, V to X, X to U, u2v v2x, u2v v2x, x to u of length 3. Yeah, so here A to C, A to C, C to D, D to A. So here I am considering, A to C, C to D, D to A. So this is of length 3, that is correct. And similarly that cycle is formed here, U to V, V to X, X to U. So which is of length 3. Similarly, I have considered one more example here where it preserves the path A to C, A to C, C to D, D to B, B to, this is a path, right, A to B, A to C, C to D, D to B, right. Similarly here U to V, V to X, X to W, it is a path. So both cycle and path are similar in both the graphs. So we can tell that both graphs are isomorphic graph. So same thing is explained here. So here two graphs G1 and G2, right, are isomorphic to each other if there exists one-to-one and onto correspondence between their vertices and also between their edges, such that their adjacency of vertices is preserved. This is very important. And G1 and G2 will have same number of vertices, they will have same number of vertices and same number of edges. Symbolically we can call that as V of G1 is equal to V of G2 and E of G1 is equal to E of G2. G1 and G2 will have same degree sequence. So G1 is isomorphic to G2. Let us solve these this problem, whether let us check whether this two graphs form isomorphic. Right. So here I have graph G1, G1 contains 4 vertices and G2 also contains 4 vertices. Let us check whether it forms an isomorphic or not. So first step what we need to do here is, first we need to check whether both the graph contain same number of vertices. Right. So here G1 contains 4 vertices and G2 also contains 4 vertices. So I have written here V of G1 is equal to 4 and that is equal to V of G2, and edges of G1 is equal to 3 and that is equal to edges of G2. So here in the graph G1 we have 3 edges and in graph G2 we have 3 edges. So that is equal. Both the number of vertices and number of edges are equal. So now we need to check whether these vertices and edges, they are one-to-one correspondence, right. So now I am mapping V1 to V1 dash, V1 I am mapping to V1 dash, V2 I am mapping to V2 dash, V3 mapping to V3 dash and V4 mapped to V4 dash. So it satisfies the one-to-one and onto correspondence, right. So next we will map the edges, right. So edge V1 to V2, edge V1 to V2 I am mapping to V1 dash to V2 dash, V1 dash to V2 dash. Similarly edge V2 to V3, V2 to V3 I am mapping to V2 dash to V3 dash, and V3 to V4 we are mapping here to V3 dash to V4 dash. So the edges are also one-to-one correspondence and they are preserving the adjacency. So now let us check the degree of a given graph. So we know the degree of a given graph. What is the degree of V1? V1 is having the degree 1 and V2 is having a degree 2, V3 is also having a degree 2 and V4 is having a degree 1, that is 1, 2, 2 and 1. So the same degree is being preserved in G2, right. So V1 dash is having 1, V2 dash is having 2 and V3 dash is having 2 and V4 dash is having 1, right. So it preserves the degree as well, right. Then we can tell that G1 is isomorphic to G2. So given two graphs, so first you need to check whether the number of vertices in G1 is equal to the number of vertices in G2, and then we need to check one-to-one correspondence, one-to-one and on-to correspondence between the vertices and the edges, and we need to check whether the degree of G1 is equal to the degrees of G2, means the degree sequence, if they are similar for both the graphs, then we can tell that the graphs are isomorphic. So let us take one more example here. So I have taken a graph here with 4 vertices and another graph with 4 vertices, right. This is G and this is H, right. So here V of G is equal to 4, which is equal to V of H. E of G is equal to 4 edges, number of edges is equal to 5, which is equal to the number of edges in the H graph, right. 1, 2, 3, 4 and 5. This is E5, right, and here 5 edges, right. So it satisfies this condition. So next we need to check for one-to-one correspondence. A is mapped to V, A is mapped to V, right, and B is mapped to U, B is mapped to U, D is mapped to W, D is mapped to W, and C is mapped to X. So one-to-one and on-to correspondence of the edges, and similarly one-to-one and on-to correspondence of the vertices. Now we need to check for the correspondence of edges, right. AB is mapped to V comma U, AB is mapped to V comma U, so that is E1 is mapped to E1 here, and E2 here in G graph, in graph G is mapped to E2 here, and E3 is mapped to E3 here, E4 is mapped to E4 here. So there is one-to-one correspondence, and E5 is from B to C and E5 is from U to X. So there is one-to-one correspondence with respect to edges as well. Now let us see the sequence, degree sequence. So A is having 2, right, and B is having 3, and D is having 2, and C is having 3. Similarly here, since A is mapped to V, we need to consider first V, right. V is having 2 and 3, U is having 3 and this is having 2, W is having 2 and X is having 3. So the sequence 2, 3, 2, 3 so is similar in both the graphs. Then we can tell that the two graphs are isomorphic. So now let us see the next example. So here let us check whether these two graphs are isomorphic. So first thing what we need to do is we need to map the vertices, right. So here each graph has 6 vertices. So graph A is having 6 vertices, and graph B is also having 6 vertices, and graph A is having 9 edges, and graph B is also having 9 edges. Now we need to check whether these two graphs are isomorphic. So here graph A, so if I consider graph A, so A I am mapping it to U. So if I am mapping A to U, A is having 2 edges, right, 2 adjacent edges, even U is having 2 adjacent edges, so I can map A to U, right. And the next I'll consider D. D is having 2 edges, right, degree 2. So I am checking degree 2 in this graph. So here X is having degree 2, so I can map D to X. Next here Z is having degree 2, right? I am trying to map that degree 2 here. So, here I cannot map in graph in figure A to any of the vertex, right. So, here though it has same number of vertices and same number of edges, the degree is not matching with all the vertices. So, these two graphs are not isomorphic. So, here one more example, that is here I have two graphs, right. One is figure A and figure B. Here I have 1, 2, 3, 4, 5, 6 vertices, right. Here also we have 6 vertices, 3 plus 3 here, D, C, E, 6 vertices, right. And the number of edges in figure A is equal to the number of edges in figure B, right. And if we consider the sequence, that is the degree sequence, A is having 3, B is having 3, F is having 3, C is having 3, and here E is having 3 and D is having 3. And here also you can make out all the vertices are having degree 3. So, since they have all the number of vertices is equal to the number of vertices in both the figure, and number of edges are equal to number of edges in both the figure, and the degree sequence is matching in both the figure. Hence, we can tell that these two graphs are isomorphic. Thank you.